Okay, so today we're going to talk about finding sample sizes for confidence intervals. Confidence intervals have a certain width to them. Obviously, if I told you tomorrow that the temperature was going to be somewhere between, say, 50 and 90 degrees, it's not really useful information. You might want a narrower interval. And one of the ways we can control to make an interval more narrow is to modify the sample size. So let's take a look. High school students who take the SAT exam a second time generally score higher than the first try. Past data suggests that the score increase has a standard deviation of about 50 points. So they're giving us there a population standard deviation. And that's good because that means we could do a one sample Z interval. That's a good thing. How large of a sample? So it says right here, how large of the sample of high school students would you need to estimate the change in SAT score within 2 points? So they're asking for N. Okay. And since we want to be within 2 points, what we're really saying in our confidence interval is that you want this part of it, which I've called before the margin of error, but you should know that that's called the margin of error. I'll just say ME. We want that margin of error to be less than or equal to 2. So I'm going to write that this way, Z star times standard deviation of population over the square root of N is less than or equal to 2. That's what we're looking for. So let's see, we expect N to be missing here, so that's not a surprise that that little N is gone. We do know the standard deviation though is 50, so I can put 50 up here over the square root of N, less than or equal to 2. And then if we want a 95% confidence interval, then we also know how to do that. We've done this before. Draw a normal distribution, put 0.95 in the middle of this thing, and then we need the area in the tails. So if we do that, we'll do 1 minus 0.95 and divide by 2 because of the symmetry. And you'll know that the area in this tail is 0.025. Some of you probably had that memorized already. Well, then you can go look in a Z-chart reverse, or you could use inverse norm on the T84 calculator and type in 0.025, and you will get back that Z equals negative 1.96. We'll use the positive version of that up here, and that's it. So the only thing left to do now is to solve this equation for N. So let's go through the steps, and then at the end I'll type it in. I'm going to divide both sides by 1.96, so we'd have 50 over the square root of N is less than or equal to 2 over 1.96. And then I'm going to multiply the whole equation by the square root of N. So I'd get 50 is less than or equal to 2 over 1.96 times the square root of N. And then you can tell that you wanted to try and get that square root of N alone. So the next step I'll do, it'll be 50 divided by this whole expression, 2 over 1.96 is less than or equal to the square root of N. And then finally, we'll just square both sides. So we'll know that 50 over 2 divided by 1.96, and that whole expression squared is less than or equal to N. And then this will give us a boundary for what N needs to be. So let's type that into the calculator, see what we. This turns out to be 2401 is less than or equal to N. So as long as we say, oh, let's write it the other way, probably people are probably more comfortable with that. As long as N is 2,401, say, samples or people chosen or more, then we know our margin of error will be small enough and our confidence interval will have a width less than 4. Okay, turns out this problem was about means and one sample Z intervals. You can do the same thing with proportions. Let's take a look at another problem here. PTC is a chemical that sometimes is in food. It says, is a substance that has a strong bitter taste for some people and is tasteless for others. The ability to taste PTC is inherited I heard the same thing's true with cilantro. There's people who can't taste cilantro. Uh, it says here about 75% of Italians can taste PTC, for example. You want to estimate the proportion of Americans who have at least one Italian grandparent who can taste PTC. How large a sample must you use to estimate the proportion within 0.04? So now we have another margin of error that we want to be less than a particular number. Remember, for a one proportion z interval, this is the basic format of that kind of confidence interval. So there you have it. We want just this part of it to be less than or equal to 0.04. So that's what we're solving. 90% confidence, so that's a new one. So let's just draw a quick normal distribution here. We'll put 0.9 in the middle. We got to get the area in the tail here, so that's going to be 1 minus 0.9 over 2, or 0.1. I'm sorry, 0.05. And then if we do inverse norm or look up the z-score that goes with that, you will get z equals negative 1.645. We'll use the positive version of that. So here we go. We'll have 1.645 times the square root of, and they gave us a p hat here. They're telling us to use this 75%, so that's convenient. So I'll put 0.75 here. 1 minus 0.75 is 0.25 over n is less than or equal to 0.04. And this is a good thing because we have everything except n, so we can start to solve. I guess we'll go through the steps and see what we get. So first thing I do is divide by 1.64. So we'd have 0.75 times 0.25 over n square root less than or equal to 0.04 over 1.645. Looks like we want to square both sides now. So 0.75 times 0.25 over n is less than or equal to this whole expression squared. So that's looking pretty good. We're going to need more space here, obviously, so we'll keep going. I'm going to multiply the whole thing by n to get that n out of the denominator. So if we do that, we end up with 0.75 times 0.25 is less than or equal to this whole crazy thing times n. And then finally, we're going to divide by that whole crazy thing. So we end up getting 0.75 times 0.25 all over 0.04 over 1.645 squared is less than or equal to n. Let's type that in the calculator and see what we get. So this turns out to be about 317.11. You're going to want to round up here because if we round down to 317, then n is going to be just a little bit too small to make this margin of error small enough. So what we end up saying here is that n has got to be greater than or equal to 318. So that's what we have. Okay. So what you'll notice is there's a part B to this question, and they're asking us, what if we use the conservative guess of p hat equals 0.5? So that's an interesting question. All right, so everything gets done the same way, except instead of using p hat equals 0.75, you get p hat equals 0.5. So you would have here 1.645 times the square root of 0.5 times 0.5 over n is less than or equal to 0.04. And you'd proceed and solve this in the same way. If you were to do that, you would get n is greater than or equal to, let's go calculate that for you. You end up getting a number of 422.82 or abouts. So n would need to be greater than or equal to 423. So you'll notice by using this other p hat, we end up with a bigger value of n. It turns out if you use p hat equals 0.5, then that will always yield you the largest number for n. You can kind of see that because in the numerator of this standard deviation, If you take any other two decimals that add to 1 and multiply them, you'll get a number less than 0.25. So for example, you have 0.5 times 0.5, and I'm doing that because it's always p hat times 1 minus p hat in the numerator. Well, that's 0.25. If you tried, for example, let's say in the case we had today, we had 0.75 times 0.25. You multiply that, you get 0.1875. So you notice that's less than 0.25, which is why when we solved and did all our algebra, we got a smaller value then. If someone thinks, well, all right, well, let's make a really big one, 0.9. And here's that push and pull, so to speak. Like if we use this to be 0.9, then the other one turns out to be 0.1 because you do 1 minus p hat. And that turns out to be 0.09, which is way smaller. So that'd yield an even smaller n. So what statisticians sometimes do is they like to use p hat equals 0.5 because it's the most conservative p hat to use. It'll give you the biggest n. If you can satisfy that n, then it'll work for any other constant interval. It's so special that sometimes it's called p star. P star equals 0.5. Okay, so let's look at one last problem. And I'll just say this. Sometimes they force you to use that p star. So you want to design a study to estimate the proportion of students at your school who agree with the statement, the student government is an effective organization for expressing the needs of students and to administration. You're going to use a 95% confidence interval, and you'd like a margin of error of 0.05 or less. So again, this is a confidence interval for proportions. This is your general format, like this. They want to be within 0.05 of the true proportion, which means that this whole thing here, again, which is called the margin of error, that needs to be less than or equal to 0.05. So let's plug in what we know. 1.96, because it's 95%, square root over n. I'm putting n there because I know it's going to be missing, less than or equal to 0.05. And I'm a little bit surprised because there's no p hat given in this problem. And so here's the rule. We just showed why in the previous slide. When you don't have a p hat, use p star equals 0.05 when p hat is missing. And we know why, because that's going to give us the biggest value of n. So if we solve for a value of n that works here, it'll work in every other problem. Okay, so you already know how to solve this if you follow the algebra on the other page. Previously in the video, you would see that n is going to be less than or equal to, let me go type this in the calculator for you. Oh, sorry, that I should just, let me correct one thing here. It should be n is greater than or equal to, just one subtle difference there, greater than or equal to, you'll end up getting 384.16 if you don't round too much as you proceed. So we would need n to be greater than or equal to 385. Okay, all right, thanks for watching.